Hi everyone. In this video, we are going to look at how to calculate the discrete random variable probability distribution. In the last video, we briefly mentioned what a random variable is. So here is the definition, basically. A random variable is a variable whose values depend on the chance. In other words, first, it is a variable like x, y, z, those letters you see in the algebraic equations. And the difference is that we still have those x, y, z's as a variable, but this variable called random variables, their value depend on chance. In other words, nobody knows the value of that variable until you see the outcome. It depends on chance. So there's uncertainty in it in terms of the value of the variable. A random variable or random discrete variable is one that you have finite number of values. You don't have anything as a value or all countless numbers as a value. You only have a finite number of values that can be assigned to this variable. On the other hand, a continuous random variable can take countless values. So let's look at some examples of these two kinds of random variables. The first one are the examples of discrete random variables. Let's see some examples here. First, the variable that represents the shoe size. So this is our first example. Think about the shoe size in the real life. We only have several, maybe just a dozen also number of shoe sizes, right? We don't have many countless shoe sizes, right? For men's shoe, and I remember I saw in the store from 8. I don't know if there's anything lower than 8. I'm pretty sure they are, but I never seen one. But like 8.5 inches. And then we have 9.5, up to, from my experience, up to like 13, maybe more. But nonetheless, just a few of them. You don't have countless of them. You don't have 1 trillion different shoe sizes, right? Even 1 trillion is still countable, still finite. You get an idea. Another way to determine whether you have discrete random variable or not is by doing this experiment. If you can insert many numbers in between any two given numbers, it is a continuous variable. Usually, for a discrete variable, you cannot insert number in between. Sometimes even if you can, you cannot do many, just a few maybe. That's characteristic of being a random discrete variable. Inserting number in between sometimes totally make no sense. For example, you have two different shoe sizes. One is 8, one 8.5. How about I input some number in between? I want to have a shoe size that is 8.1235. Does that make sense to you? Think about that. Also, another one is, let's look at next one. Maybe now we have a couple of examples here. Next one, a random variable that represents the number of people in the classroom. Or this one even more telling, even more, easier to identify that this is a discrete variable, because no matter how many people in the classroom, no matter how big the classroom, it cannot hold infinite number of people. The number of people in there is finite number. That means this variable can only take a finite number of numbers. Maybe it's just 10, maybe 100, maybe even 1,000 in the big conference room. But 1,000 is still a finite number. You're not going to have countless number of people in the classroom. At the same time, think about that. This variable represents number of people. Can you insert a number in between two numbers? For example, between 10 and 11 people, can you insert another number in between? Like we have 11.5 people? Doesn't make sense anymore, right? So that's one of the characteristics of a discrete random variable. You cannot just input numbers in between. It doesn't make sense. Now, another example, the third one, a random variable that represents how many cars you have in your household. Again, no matter how many, just a few possible numbers. Even maybe you have 0 cars, you don't have cars. Maybe you have 1, maybe you have 2, maybe you have 5 even. For car collectors, maybe that person have 1,000. No matter what, you just have a few number possible for this variable to take. No more than that. Plus, you cannot insert number between two whole numbers. Like I have 1.25 cars. That's totally insane. Okay, you get the idea what is a discrete random variable. On the other hand, as a comparison, continuous variable is a variable that can have infinite possible values. No matter how small, how big, in between, you can always insert as many numbers as you want. There's no gap in between any two numbers. For example, time is continuous. Can you imagine time is like just a gap in between? We cannot imagine that. This never happen. If it happens, something terrible going to happen. For example, how about we go from 2 o'clock p.m. to 3 o'clock p.m. without nothing in between, just jump to the 3 o'clock? It's not going to happen, right? Even if between the current, this second and next second, there are many milliseconds, nanoseconds, or even smaller unit of seconds in between. We just don't have that unit to measure it because we don't need to measure it. It's too short. But nonetheless, you get the idea. Just countless numbers in between you can insert. No matter how small the interval, you can still insert infinite number of numbers in between. That's called a continuous variable. So some examples for continuous variable. And the variable that represents the time, I just mentioned that. Let's look at the next one. The variables that represent people's height. Again, even though we see the people have different heights, right? Say 5 inch, 5'11", 5'10", 5'11". How many people in between? Countless. We don't really know. In theory, just really countless. Even though we don't have countless people, but in terms of height, because height from 1 inch grows to next inch, there's no gap in between. If there's an even tiny gap in between, I can ask you this question: where are you at that moment? When you have that gap, where are you? Think about that. So height is continuous variable because it's grow a little bit by little bit, tiny bit by tiny bit, and over the time you see the difference in height. But with very small unit of time interval, you don't see any change. Actually, it's changing all the time. It's just too small. We don't see it. That's why it's continuous. Okay, after we understand these two basic types of random variable in probability, now let's look at another terminology. And this one is called probability distribution. Now I'd like you guys to recall what you learned in Unit 3, where we had frequency distribution, right? Frequency distribution. And in that part, we learned that we can use a table to represent frequency distribution. We call it frequency distribution table, right? In that table, we have two columns. The first column is the events or category of values. The second column is frequency itself. Now, when we do this probability distribution, it's very similar to the frequency distribution. We also have two columns in this table. The first column is still events or values like people's heights or other whole number values like how many cars you have in a given household, right? In the second column, we don't have frequency. In the second column, instead, we have a probability. In other words, probability distribution just tell you how likely each value can occur. For example, given a city, how likely for any random household to have two cars, two vehicles. So 25%, 30%, whatever the number is, that's likelihood, right? Instead of frequency, you get likelihood. That's called probability distribution table. Now, this is how we calculate probability. This is called theoretical probability, but in this course, theoretical probability is only type of probability we deal with. So for that matter, you don't need to worry about that theoretical, that word too much, just call it a probability. Now, it is calculated using this general formula, even though later on we have a more complex probability calculation problems, but the basic structure in terms of calculating probability remains the same. It goes like this. This is the event. For example, what is the probability of having two cars? Having two cars is an event. So, and the probability of this event to happen equals the number of outcomes in that event. In other words, on the top, you have a desired outcomes, total number of desired outcomes. If you're looking for two cars, you want to know how many households in a given area has two cars. And on the bottom is total number of possible outcomes. So basically, in the end, you just do division after you have these two numbers to get a probability. Now, before we go into too deep in terms of details, let's look at some basics so that we establish some foundation before we do any calculation. For this formula, you're going to see more concrete example to illustrate the meaning of this formula. So for now, don't worry about this too much. You're going to realize this is true in a natural way. First, we want to know as a part of the foundation that any probability value is always between 0 and 1. In other words, probability value is a range, and that range is between 0 and 1, including 0 and 1. Never go out of this range. If you get a probability of 74, something terribly wrong. And so we have this basic knowledge so that we don't make ridiculous mistake when we calculate probability. Okay, now first, this is about how to represent a discrete random probability distribution. Basically, there are two different ways to represent the probability distribution. Later on, we do calculation itself. And for now, I mentioned in the previous slides that we can use a probability distribution table, and this is the example actually. You see in this table, we have first column, which is events, and that's a general name. When you create a probability distribution table, you want to label your columns in specific meaning, using specific meaning, so that the readers will know the meaning of this table. What is this table about? Otherwise, if you use two general words, people still don't know what these numbers mean, even though they know this is a probability distribution table. So let's read this part of description. It says random x, usually random variable x, usually variable itself, we use a capital letter, and the value, those values to represent those variable values, we use a lowercase letter. This is a general description of that variable. We have this variable x, which represents the number of siblings of randomly selected student. Now, let me give you a little bit background information. Basically, this is in a group of students, and they already know in advance by asking those students how many siblings they have, each of the students. And this, after they do that survey, they draw the conclusion that some students don't have any siblings, which means 0 siblings. And the most siblings one student can have in that group of students is 4. As a result, the possible values for this random variable x, which represent number of siblings, ranges from 0 to 4, because we already established the basic fact about that group of students. They just have either 0 or through 4, no more, no less. This is just within that range. So as a result, this random variable, take 5 different numbers, finite values. That's why it's discrete random variable. At the same time, you cannot have 1.5 siblings, right? You cannot insert a number in between. We say the discrete variables, that part is easy to understand now. How about random? Random is not that the value that this number can take it will never be known. That's random. It's not that random. We already know the range of these values, either 0, 1, 2, 3, 4, one of this. But when we say random, it really means this. If you randomly select a student, you don't know how many siblings that student will have until you actually select that student and ask him, hey, how many siblings do you have? Then you know the answer. At that time, it's certain. Before that, when you randomly select one, you don't know how many siblings that student you're going to have, because you don't know which student you're going to choose actually, because randomly select student, any student can be selected. As a result, you don't know the result before you select a specific student. For that reason, we call it random. Now, second column is a probability column. How do we read this table? Say, take the first one as an example. This is the value, this is the probability. In other words, in that group of students, if I randomly select one, remember, randomly really means everybody has equal chance to be selected. If I random select students, there's 20% of chance, 0.2 equals 20%. There are 20% of chance that student has no sibling. That's the meaning of these two numbers. Say x equal to x, this is random, this number of siblings equals x, this is smaller x, that means when your x equals 0, probability is this. When your x equals 2, probability is this, which means that if you randomly select a student from that group of students, there are 27.5% of chance that student have 2 siblings. That's how we read this table. And 2 characteristics of a probability distribution table. First, each number has to be no bigger than 1, between 0 and 1. That's the basics. I just established that, right? Probability value is always between 0 and 1. And secondly, there's another characteristic. The sum of all of the probabilities have to be exactly 1, no more, no less. Just like the sum of all relative frequencies will be exactly 1. We learned that in the unit 3. Okay, probability being 1 means it will happen. When you add them together equal 1, that means all of this. So if you select student, I'm sure, 100% sure, the student will have anywhere between 0 and 4 siblings. It's not going to be outside this range. You know that's true, right? That's why when you add them together equal to 1. Okay, so table is the first form of discrete random variable probability distribution. It could also take another form. We call it histogram. Histogram is kind of similar to the bar graphs. Only difference that for histogram, you can see here, there's no gap between bars. And for a bar graph, there's a gap between bars. But for our probability representation, discrete variable probability representation, don't worry too much whether you have gap or not. Basically, they give you the same amount of information. So it's not concerning here. Now, let's say basically this one just a visual representation of the table on the previous slides. Let's look at the second one. 42.5% have one sibling, right? Let's look at this bar graph or histogram. Horizontal one is a number of siblings, just like frequency distribution table. Horizontal one represent first column. So this is the first columm. And the second column, if this is a frequency distribution table, it would be frequencies. But instead, this one is a probability, also second column. Notice that it's all smaller than 1, right? So we mentioned that we have about 42.5% of all students have one sibling. Look at that, one sibling, say number of siblings. Look at how they label the axis. They don't label this as a something like a class intervals, right? These are frequencies. You have to use some specific meaning so that people can read this chart to understand the meaning of this chart. So this is number of siblings, and this is the probability. So if we look at the one sibling, the height is like between 0.4, 0.45. That's 0.425, right? 42.5% chance that a selected student will have one sibling. So this is exactly the same information, just represented differently. So now let's summarize this before we move on to the next one. So for a probability discrete distribution, discrete variable probability distribution, there are two forms. One is frequency, one is, I keep saying frequency. One is a probability distribution table, one is a bar graph or histogram. And in that frequency distribution, I hate myself now. In that probability distribution table, each probability value has to be between 0 and 1, and the sum has to be exactly 1. Okay, now we can move on. Summarize. Then we look at some exercise problems. And keep in mind that each probability value should be between 0 and 1. Secondly, the sum of all probability values in the distribution has to be exactly 1. So I cannot overemphasize that. I'm sure, I guarantee that no matter how I emphasize this, there will be students who still get something like 12, 74, 100 something as a probability, even though we clearly say it has to be between 0 and 1. Okay, some exercise problem. Let's do this one by one. Does the following represent a discrete probability distribution? How do we tell? Remember, for a discrete probability distribution, it can only take two forms. Either you have a table, apparently this is not a table, or you have a histogram or bar graph, right? So we do have a bar graph, looks like, and this is okay. It can be anything horizontally, it's just events. Now look at the vertical one. First sign that this is not a probability distribution is because this is not even probability. If it is not probability, how can you call it a probability distribution, right? Secondly, look at these numbers. Any probability value has to be between 0 and 1. Look at this. Each one of them is way over 1. So this is not a probability distribution, later on discrete one. It's not probability distribution in the first place. Second one, does the following represent a discrete probability distribution? This one even faster now. Why? Only two forms. Table, this is not table. Bar graphs or histogram, this is not bar, this is not histogram, and that's it. We don't even need to read details. Answer is not. Now, next one, this one is more challenging. Let's say if you answer this by yourself, try to imagine that if you can answer it correctly. Does the following represent a discrete probability distribution? Again, for a discrete probability distribution, it takes two forms. A table, a histogram, also called a bar graph. Either way is okay. But apparently this is not bar graphs, right? So this looks like table because whenever you have rows and columns, it looks like table. No matter you draw those rows or column or not, as long as you have rows and column, it is table. Okay, it is table. So that part we pass is table. Now this event values, this is totally okay. Second one looks like probability, looks okay too, because they're all between 0 and 1. Is it? I mean, is this can we determine this is a discrete probability distribution? The answer is no, not yet at least. The reason that's not a requirement. The sum of all of the probabilities have to be exactly 1. When we add them together, when we add them all together, I got 0.1 or 0.98. So answer is no. Just be careful. That's why we need to do exercise to help people understand completely the definition of discrete probability distribution. Okay, another one. This time is calculation problem. A math professor. This one I remember I pulled it from a homework session, so it should be very similar to the ones that you're going to see. A math professor has office hours from 9 a.m. to 10 a.m. each day. The table below shows the probability associated with the number of students waiting to see the professor. So what this means, let's understand the meaning of this. So apparently this number of students waiting can only take 6 values, discrete, right? Find the number of numbers. And secondly, and when we say 0.05 is the probability, what does this mean? That means on any given day between 9 a.m. and 10 a.m., there's a 5% of chance there will be no student waiting to see the professor. And that's the meaning of that. Okay, now we can answer questions. Now, the way you answer questions, always pay attention to the requirements. There are always students who lose points on the homework because they ignore or they didn't see the requirement. For example, they require percent, people put in the decimal number, and when they require 2 decimal digits, people put in 1 or 3, and that kind of things. So, example, there is 25% of chance that 3 students are waiting on a given day between 9 and 10 a.m. In other words, they want you to answer question in terms of percent. Okay, look at this. We do this one by one. Let me cover the rest so that we can focus on these questions one by one. What is the probability that at most 3 students are waiting to see the professor? First, this is the boldface. We want to understand exactly the meaning of at most. At most means no more than, up to 3. That means including 0, 1, 2, 3, at most 3, no more than 3. That means remember the basic formula to calculate the probability using the desired outcome divided by the possible total outcomes, right? So total possible outcome, we have this 1, 2, 3, 4, 5, 6. They're all possible to turn out how many students waiting, right? Which one are desired one? These 4 numbers are desired one because we are looking for the probabilities that represent this kind of outcomes. If we have not student waiting, that's fine because that's smaller than 3. 1 is fine, 2 is fine, they're smaller than 3. 3 is also fine, 3 equals 3. It's no more than 3, at most 3. So all of these results are desired. So when we calculate probability, we have this basic formula for the OR probability, and that is, we call it P, A or B, right? We learned that in the unit 3. Basically, if A and B are exclusive means they don't happen at the same time, then the probability of all events will be just the sum of these 2 probability for these 2 individual events one by one. And this can be expanded to more than 2 events. As long as they are exclusive, you just add them all together. And that is the case for us. No matter how many students show up in that given day at that moment when the professor saw them, there's only one number, either 0 or 1 or 2 or 3 or 4 or 5. You cannot have 2 numbers show up at the same time. That's just insane. It's not on Earth, right? So these numbers are not going to happen at the same time. So they are exclusive events, and we do OR. So in other words, we just need to add them together. We are doing probability to getting 0 or 1 or 2 or 3. And even though we write this as probability to get less than or equals 3. Let's use X because X represents number of students, represent that random value. X smaller than or equal to 3. We write it this way, this really means either 0 or 1 or 2 or 3. So we just add them together. 0, 1, 2, 3. This is for the teaching part. Once you understand that, all you need to do, add this together. Actually, that's easy to do. So let's say what we get, 0.05, 15, 15, this is 40, 80, 80%. That's final answer. Actually, there's another way to do this faster. Since we want this 4, we don't want this 2, right? The whole thing is always 1. Remember, we add the whole thing together, probability is always 1. You can use 1 minus this 2 to get this. This 2 is 0.2, right? 1 minus 0.2, 0.8 is easier. So that's the first one. Second one, this is number 1. Number 2, what is the probability that less than 2 students are waiting? Less than 2. So number 2, let's put it here. So we're looking for x less than 2. Yeah, less than 2. Less than 2, how many values less than 2? 1 and 0, right? So we just put these two together. Equals 0.05 plus 0.1. So 0.15, which is 15%. 15%. In other words, on any given day, there's a 15% of chance the professor will see either no student or just 1 student. That's a chance to see this kind of situations. Now, third one, what is the probability that more than 4 students are waiting? More than 4. There's only one number more than 4, right? This is what we're looking for, more than 4. So direct is 5%, 0.05. Only 5 is more than 4. So it's very easy to once you understand that. Let's continue. Another one. Basically, the description is exactly the same. This table is even exactly the same. We just have different questions here. So let's go to the question directly. What is the probability that an even number of students are waiting to see the professor? So basically, this x is even number. How many even numbers? That depends on the if students are clear about the definition of an even number. An even number is a number that can be divided by 2 evenly. 4 can be divided by 2 evenly. 2 can be divided by 2 evenly. How about 0? 0 divided by 2 is 0. It's even. There's no remainder. There's no decimal. So we have 3 numbers, and 0, and 2, and 4. So 0.05 plus 0.40 plus 0.15. These 3 numbers add together. This is a 20, this is 40, totally 60. So 0.6, and that is 60%. So on any given day between 9 and 10 a.m., the professor has 60% of chance to see an even number of students waiting. Now, second one, what is the probability that at least 3 students are waiting? At least 3. That means minimum number of 3, cannot be less than 3. That means starting from 3, 4, 5. So second one here, we do at least 3. This is how we represent that. This value, at least 3 means no less than 3. That means could be bigger than 3, could be equal to 3. So how many? 3, 4, 5, right? We get 0.25 plus 0.15 plus 0.05. This is 40, 45. So 45%. 45%. So in this case, this professor better not to be late, because there's almost 0.5% of chance this professor on any given day could see students from 3 to 5. If you have more students waiting and you're not showing up, and that's an issue. At least, especially when it is a repeating issue, that's a serious issue then. Now, next one. Pretty much this is the last one, I believe. Yeah. When pets enter an animal shelter, a variety of medical tests may be needed. The discrete graph below, say we have bar graph here, shows the probability associated with the number of tests that a pad may need. So in other words, horizontally, in a histogram of frequency bar graph, the horizontal axis represents the value of that random variable, and vertical one represents the probability, right? So this is a number of tests, either 0, 1, 2, 3, 4. That means it could take any of this value, but not out of this range. Now let's look at the question. The first one, what is the probability that a pad may need less than three tests? In other words, X represents test. We are looking for the probability of this when they enter the shelter. Now, basically, remember, this is just another form of probability distribution, just like a table. There's no difference as long as you read it that way. So we're looking for less than 3 for this value, test number of tests. This one is less than 3. We take this one less than 3, this one less than 3. So we just need to read these numbers and add them together. Let's be careful. Start from lower value. We have 0.2 for 0 test. And then 1 test is 0.3. Add them all together. And 2 tests is 0.35. So we still need a percentage as the answer. So this is 5, the half, this is 85. So 85%, 0.85. So for any path randomly selected, that path has 85% of chance to get less than 3 tests, less than 3. So you see, once the value reaches 3, the chance to the probability is much lower. That means the chance for any given pair to need 3 tests is very low, 4 even lower. Except that pair is really special, really a mess. Basically, that pair will need so many tests. Okay, exercise. I do this in the face-to-face class, exercise problem. So we do this as an example in this video. What is the probability that a pad may need at most 2 tests when they enter the shelter? Basically, they just play this word game to see if people understand exact meaning of all this kind of words. At most 3, that means no more than, I mean 2. At most 2, no more than 2. 2 is included at most. Okay, that means 0, 1, 2. So we're looking for this number of tests at most no bigger than 2. That means smaller than or equals to. That's how you write that. Smaller than or equals, what do we got? We don't need to do anything. This is exactly the same. Just different way to say that. This is smaller than 3. This one said no more than 2. This is exactly the same thing. So 85%. Okay, see you guys in the next video.